Today our topic is the colligative properties, and colligative properties is a separate segment of this chapter. So it's a new term for all of us. So let us try to understand what is a colligative property. If we want to define, the definition will be like the properties of a solution which only depends on the amount of solute or the number of solute, but it does not depend on the nature of the solute. So the amount or the number of solute becomes the important factor over here. There are four colligative properties which we need to understand under our syllabus. One is the relative lowering of vapor pressure, one is the elevation of boiling point, one is the depression in freezing point, and the last one is atmospheric pressure. So here let us see one by one, although we have discussed the relative lowering of vapor pressure in our previous discussion. Among the colligative properties, the first one that we will discuss is the relative lowering of vapor pressure. Remember, we have already discussed about it in our previous video, but just for a reminder, let us understand this once again. Suppose we take a non-volatile solute. Suppose we take a non-volatile solute. Suppose B. And suppose we take a solvent which is A. Now, if xp is the mole fraction of B and xa is the mole fraction of A, as we know that the solute is non-volatile, so there will be no contribution of solute to the vapor pressure. So therefore, whatever the total vapor pressure of solution will be generated, suppose that is P, we can say that P is equal to PA because it is completely the vapor pressure of the solvent alone, because the solute will have no contribution. So as we know, PA is equal to PA naught into XA. So we should also be able to write that it is equal to P as well. Now, as we know that the mole fraction of A is always less than 1. So vapor pressure of the solution is always less than PA naught. So here we should be able to write is that the change in vapor pressure, that is delta P, is PA naught minus PA. Here we can write PA naught minus the PA naught into XA, as we have already written. So we can take PA naught as common, and it can be 1 minus XA. If it is a binary solution, we should be able to write XA plus XB is equal to 1. So 1 minus XA is nothing but XB. So here we should be able to write that delta PA is equal to PA naught into XB. So the delta PA divided by PA naught should be is equal to XB. In other words, what is delta PA? It is nothing but the difference between PA naught minus PA divided by PA naught is equal to XB. Let us try to understand it once again. This is the vapor pressure of a pure solvent. This is the vapor pressure of the solvent after forming the solution, which is equal to, here you can see P is equal to PA, so it is compared to P and divided by PA0, which is again the vapor pressure of the pure solvent. So this much is the amount of lowering. We have earlier mentioned it here. Here you can see. Since it is divided by PA0, once again it is called the relative lowering, and it is depending on the amount of solute only. It is depending on amount of solute only. That is why it is not depending on the nature, and it is a colligative property. In the next topic, we are going to learn about the determination of the molar mass of solute from the relative lowering of vapor pressure. So let us rewrite the equation coming from the relative lowering of vapor pressure, that is Pa naught minus Pa divided by Pa naught is equal to Xp. Now, if we consider that Wa and Wb are the corresponding weights of the solute and solvent, these are the weights of solute and solvent respectively, and the number of moles for A it is Na and for B it is Nb. If we consider this, then we should be able to write Xb is equal to obviously the number of moles of B divided by the total mole, which is Na and Nb, because there are only two type of components. So we know that Na, it is the given mass by molar mass, and Nb also Wb by Mb. Now Xb, we should be able to write Wb by Mb divided by Wa by Ma plus Wb by Mb. Now, let us try to understand that this law is applicable to the ideal solution, which is very dilute. That means the molar concentration of the solute will be very small. So the molar concentration of the solute, if it is very small, we should be able to write Wb by Mb is very, very less. This is the molar concentration of the solute, is very, very less than the solvent. So in that case, this part, how we can rewrite is that Wb by Mb divided by, it should be almost equal to Wa by Ma, because this part is really smaller than this. So the addition of these two will be almost equal to this much. It should be is equal to Xp. Now Xp, we can write Wb into Ma divided by Wa into Mb. So in the final equation, which is Pa0 minus Pa divided by Pa0 is equal to, we should be able to write Wb into Ma divided by Wa into Mb. So from this equation, we should be able to calculate the molar mass of solute. The molar, remember B we are considering as a solute, so the molar mass of solute we can be able to calculate if the other values are given from here. The second colligative property that we are going to read is the elevation in the boiling point. Now for that, first of all, let us understand what is boiling point. Now boiling point, in a simple way we can say that the temperature at which the vapor pressure of the solution, temperature at which the vapor pressure of liquid becomes equal to the atmospheric pressure. So let us try to understand the situation. We know that the vapor pressure of solution containing the vapor pressure of solution where non-volatile solute is present, the vapor pressure of a solution where non-volatile solute is present, it is always less than that of the vapor pressure of solvent, pure solvent. We have just read that in the relative lowering of vapor pressure. So the solution has to be heated to a higher temperature so that its vapor pressure becomes equal to the atmospheric pressure. So we have to heat it. So boiling point of the solution is always higher than that of the pure solvent. So if the boiling point is Tb of the solution, And for pure solvent, if it is TB0, for pure solvent, if it is TB0, then it is quite obvious that the delta TB should be is equal to TB minus TB0. This much, this delta TB is called the elevation in boiling point. Now we will understand how it is shown graphically. The graphical representation of the boiling point elevation. See the two axes, the vapor pressure and the temperature is being plotted here. Now see these lines carefully. There are two lines, one is orange, one is blue. Orange one is for solvent, and obviously the vapor pressure of the pure solvent will be greater than that of the vapor pressure of the solution. So in order to match the boiling point, here you can see the 2 points where the vapor pressure will be equal to the temperature. For the pure solvent it is less compared to the solution, and later on in this graph itself we will see the difference. You can see the difference over here between those 2 points. The solution will be on the further right hand side if we are considering its boiling point. So this difference in the boiling point, which is TB and TB0, TB is clearly greater than that of TB0, and this amount is known as the elevation in boiling point. Experimentally, it is found out that the delta TB is always proportional to M, which is molar concentration. So if it is so, we should write that delta TB is equal to Kb into M. This Kb is called the molar boiling point elevation constant. So from this equation number 1, if I put M is equal to 1, so obviously delta TB is equal to Kb. So the molar boiling point elevation constant can be defined as the elevation in boiling point for 1 molar solution. That means the solution containing 1 gram mole of solute dissolved in 1000 gram of solute. Now we will try to understand that how to calculate the molar mass of solute from the elevation of boiling point. So for that we have to define molality, which is the moles of solute into 1000 divided by weight of solvent in grams. So if we want to write further, we know that moles of solute, we should be able to write WB by MB. So M should be is equal to, which is molality, should be is equal to WB by MB into WA into 1000. Why so? Because here you see moles of solute. So solute means B. So WB by MB divided by weight of solvent in grams, that we have written WA into 1000 if it is expressed in grams. Now substituting this value, we know that delta TB is equal to Kb into M. So delta TB should be is equal to Kb into M means what? WB by MB into WA into 1000. We are just putting this equation over here. So here you can see the MB is already here. So MB, that is our desired target, which is the molar mass, this part, which is the molar mass of solute. We should be able to write as MB is equal to Kb into WB into 1000 divided by delta TB into WA. So there will be lots of numericals where we have to either calculate this one directly, or this will be given using this equation we have to calculate something else. We will see those.